So our session has been started and I have started recording. I hope you can see my screen, right? Okay. So okay. So week 5 started with that concept that has been taught in the last week, that is that perturbation theory, or the interaction semi-classical treatment between what is the interaction between the particle and the radiation, and it is a continuation from there. So we have learned that there are two states. So I'll write something here. Week 5. So you tell me, you can, if you can see the writings, or do I need to write it in a bigger way? Okay. So it has been taught that if there are two level systems, suppose AM and L, where the energy of AM is obviously, as you can see, that energy of AM is more than energy of L, and if there is some transition, suppose from L to M, so ultimately due to that, after some time, so at beginning, suppose when t tends to 0 time, when the we have excited, so at that moment our capital psi, actually at the means our capital psi will be defined by this mixing of two states, as you can say, or a linear combination of both of them, Cl psi L, let me write it in capital, and Cm psi m. So these psi's are in capital. Capital psi means dependent on both time and space. And when I will write, suppose this psi is, capital psi is dependent on both this xyz space and time. So this is equals to psi, which is xyz z, and phi is dependent on t. So at t tends to 0, Cl is 1 and Cm is 0, but just after the excitation, or after some time, at time t, which is very small, after time t means some nanoseconds or something like that. So at that point, so here your psi is, capital psi is almost your Cl psi L, right? But after that, due to that perturbation theory, your some of the molecules are here and some of the molecules are in your M state. So your psi is a linear combination like that. So there Cm is not anymore 0, and how this Cm, the coefficient of psi m, varies with time, that is very important. So we have learned those things in the next in the earlier week. So we'll start from Rabi's oscillation. So what is Rabi oscillation? Rabi's oscillation, not Ruby's oscillation, as Sarah said. So it is a very common mistake we do. Rabi oscillation is that this Cm, you can see, so this Cm mod Cm square, that is actually your Cm star Cm, that is actually given by some constant of E naught x square, your transition moment integral, that is your psi m. So it is only dependent on space, your transition moment integral, as you can see, your dipole moment, psi of your initial state, and the square of that, and some sine function. Okay, I'm not going into in deep, but there is some sine function, and let me write it also. The sine square pi t nu 0 minus nu. A nu 0 is already you can see in the lectures. What is that? I will briefly tell you. This is the thing that Sarah has derived and showed that this Cm square, this is the you can say contribution or the probability of finding, right, the psi m, or the attribution of finding the psi m. So how this Cm square varies with time, that is known as Rabi's oscillation. And why oscillation? Because the sine square or the trigonometric part is there. So as you can see, so this is all a constant, and then there is a sine function. So eventually it will have a sinusoidal curve like this. So which is, suppose this is your cm square and this is your time t, and as you can see all the things are positive, right? And it is sine square, no sine, so maximum value is 1 and the minimum value will be 0, right? The minus 1, the sine value can vary from minus 1 to 1, right? But here it is sine square, so all will be positive. It will have a something like in this kind of nature. Okay, so this minima is actually 0, so it's my poor artistic skill, that's why it is something like that. But it is of a same frequency, and the frequency is actually you can say frequency, I'll say. So see, at what time it will be 0? The first 0 will come when new so let me tell you what is nu 0. Nu 0 is the energy gap between these two, em minus el, and nu is the frequency of so actually h nu naught is the energy gap between that, and nu is the frequency of light or radiation, right? Radiation with matter, the interaction we are providing, so when nu 0 minus nu, that is a resonance condition we generally say. So as you can see that the first 0 will come when nu t equals to 1 by nu naught minus nu, right? So then what will happen? Acha, have I made any mistake? I'm checking just. Acha, this I have made one mistake. So this is out of this sine thing, so I'm very sorry. So this is just a denominator. I'll write it. I'll use a eraser and come back. Wait. So why can't I use a eraser? Highlighter, eraser, but so they are not letting me use the highlighter, eraser for some reason. Let us not go. So this is the sine part, right? Sine square pi t nu naught minus nu. So when t equals to 1 by this term, then it is sine square pi, and then it will be 0, right? At t equals to 1 by nu naught minus nu, and then the next 2 pi, right? Because sine is a oscillating thing, and at n pi you will get the value of sine as 0. So here it is 2 by nu naught minus nu. So this keeps going on. So as you can see that at different t, your cm square value will oscillate from 0 to 1. So at starting it is 0, right? Because at t tends to 0, we have shown you that there is no contribution from psi m, because as you can say, it has just come, the radiation has just interacted, but it is not yet perturbed. But then the perturbation starts, and as it is a perturbation theory, which is an approximate method, so we can't take t actually to infinity. So actually what is happening, that t is actually acting between this part or very less. So can you understand what I'm trying to say? So as it is a perturbation theory, t is acting on the radiation is active or the interacting with the molecule for a very less time. It is not really t is infinity. So and the amplitude is given by, as you can see, so these are the constant is already there. So actually ex square we can write in terms of rho nu also, and your transition moment integral square psi l square, and divided by, as you can see, this is the amplitude value, a square nu naught minus nu. So when your resonance condition means nu 0 is almost close to nu, then as you can understand, as the denominator will be very less, so these will blow up. So how to get cm square high cm square you will get when you will use a high intense light, high intense or intense light we can say, not high, as you can understand, and when the transition moment integral is non-zero, right, TMI, this is also known as non-zero, and your nu 0 is close to, or nu 0 is nu or something like that, then your amplitude will blow up, right, cm square, high cm square, right, very high. And as you can see, at that point of time nu 0 minus nu 0 is very small, then you're actually what you are trying to say, this frequency, so this 0 will come, if the denominator is very less, then what will happen, this t will be very large, right. So actually what we are saying, that this this oscillation will be slow. What I am trying to say means, from 1 to 0 it will come very late. I think these are the things are very beautifully discussed by Datta sir. Do you have any doubt while reading this part? Anyone? So who are now, who has attended till now? Avantika is here, or no? Acha, both of you are here, so it's good. So Jacob and Avantika, do you have any doubts in this place? In this Ravi's oscillation part, while you're reading or something right now, if you have any doubt, you can tell me. Then we'll go to so till this part we are discussing that semi-classical treatment of light. Yes.
No.
Okay. Jacob, I hope you are following this. Actually, this,
Sir, I have a doubt.
yes.
Sir, you told it is being perturbed.
Yes.
So, from the sinusoidal curve,
Yes.
actually my cm square value is decreasing due to the perturbation effect, right?
No, first it will increase, because see, the perturbation means you are perturbing your system with radiation, and what you expect that at time 0 or tends to 0, there is no psi m, right. Psi means it is not populated, your m state is not populated.
Yes.
So what you are actually seeing this from this Rabi's oscillation part, that with time t, first it is reaching a maximum value, your cm square, the amplitude or the contribution of this psi m wave function, and then again it is coming back to 0. But
That means I am saying that my population on the m level has increased to its maxima,
yes,
and all of them emitted back.
yes, but this part you also have to see that time is not really very high. So this interaction time is very less we will keep, because this is a perturbation theory, right. So maybe before coming to 0 or something like that, we are not going that part. We are only thinking that it is going to at least some value, not 1 or something like that. I mean, we are not yet reaching the maxima. Before also it can happen. So for any time your light can interact with your the matter, right.
So you are saying the time when light interacted with matter, it reached maxima.
No, time is not maxima. So time you can vary, right, but for the
Not
perturbation,
time. The cm square reached its maxima.
yeah, it may also happen that cm square maxima, as you can see from here, is 1, right, something like that, or this value, this rho nu psi m, it could be anywhere depending on your rho nu, if the process is forbidden or not, like this. So it can also happen, may not reach the maxima, it can reach up to some value. Some value is also important, because then your aim is populated. It means that right now after interaction with light at t equals to 0 or t tends to 0, cm was 0, but it right now it has some value. It can happen that your perturbation is still up to this point or this point. It can happen anything, but it will be very slow.
Oh, the increasing slope is what perturbation is for.
Yes, you can think
Uh,
like that, how it is
okay.
oscillating. So, and for as it is a perturbation theory, and you know these are all approximation method, I think you will I think you have already been introduced to, or you will be introduced in your third year or something like that, quantum mechanics. This first order or the second order perturbation theory will be discussed. I think in our courses generally the time dependent perturbation part is not really discussed that much, and this is the effect of time dependent perturbation theory.
Hmm.
Generally in our courses time independent perturbation theory are being taught, but till then also what we generally discuss that in time independent perturbation theory, that the perturbation is very less. Okay,
Hmm.
and now
Hmm.
for time dependent perturbation theory you also have to understand the time, for how much time it is interacting with our matter, the radiation, that is also very less.
Hmm.
Okay, so next what we will go, we will quickly discuss why, so that is lecture, so these are all discussed in lecture number 21, lecture 21. So Avantika, I showed to Jacob that today we will discuss some of the rotational or microwave spectroscopic numerical problem. So we will quickly finish this thing and then we will go to there. Okay, so lecture 12 22. So in lecture 22 actually what has been discussed here, the lasers. So Jacob, can you tell me what is a laser? LAACR.
Um, light, um,
Amplified.
amplified, stimulated emission, and
Yes. So two three things are very important, right? That stimulated emission. So
hmm.
that is the term we are dealing here. So for
Hmm.
laser we will need a stimulated emission,
Hmm.
and stimulated emission will be possible when there is a population inversion. Suppose you have a so still suppose these are L and M, okay, and there will be some transition. So you will excite it and it will go to M state, but then it depends. So the absorbance process, it is known as stimulated absorbance. Okay, stimulated absorbance. So we are discussing actually, this is a continuation from Einstein's treatment. Okay, Einstein's treatment. So where he has defined a few rate laws and a few, so that was the starting point behind the CM and other thing. Anyway, let me tell you here, the stimulated absorbance, there is a coefficient of name as Einstein's coefficient of stimulated absorbance, that is BL to M. Okay, and there is some known as stimulated emission coefficient, Einstein's coefficient of stimulated emission, that is B M to L. Okay, coming back to here, so your stimulated absorbance is that you are giving it some radiation and then it is absorbing from L to M, and stimulated uh, emission is, so that is stimulated absorbance, and this is stimulated emission in presence of some stimuli, that is your radiation, it is coming back to the lower state, that is the stimulated emission. Generally we don't discuss with the spontaneous emission, this is stimulated one. Okay, so and there is something spontaneous emission, spontaneous emission coefficient, Einstein coefficient of spontaneous emission, that is known as A L to M or whatever. So till now from Einstein treatment we know that B L to M is equal to B M to L, that is B you can say, and there is some dependency over A and B, that is some constant is there. Okay, so if your B is non-zero, then your A is non-zero. Okay, means if you are absorbing something, if your system is absorbing, that means there is some B, right? B value is there, so it should also have some spontaneous emission, but that depends on different rate processes. So it is not, so your A can't be zero if your sample is being absorbed, some absorbance is there. So depending on that, it will depend that if your system will have stimulated emission or not. If suppose your all the emission is coming through the spontaneous channel, then your stimulated emission is less, right? Then we have to decide for a two level system, is it really possible to have a stimulated emission or not. And stimulated emission will be possible when your population of the PL state is less than PM state. So generally what we know, suppose these are two electronic states, right, or any states. So at room temperature or something like that, your population of the L state is always more. Suppose this is not a rotational line. So in rotational case we can say no, the population of the M is high. But suppose this is a vibronic or the electronic states. So there we can say that your population of the, normally what happens, normally at room temperature your PL is very higher than PM. Okay, now after stimulated emission your population go to the M state, and if the situation is something like that, your population of M is by population of L that is greater than 1, then you can expect that stimulated emission. Okay, so so don't worry if I am jumping some steps because these are all discussed in the science lecture. So if you have any doubt, you can tell me right now, but you can always go back to the lectures. So actually this is for stimulated emission. This is also known as population inversion. Okay, so population inversion means your PM, that is the upper state, has a higher lifetime than this, or you can say that your PM, that is by your total population, that is PM plus, where P is PM plus PL, this is actually greater than 1. Okay, then this is known as population inversion, and then you will see the stimulated emission. So what sir has discussed, that for a two level system like L and M, your rate of this population DNM, so this is the population, suppose right now instead of P, suppose this is the population of this NM is the population of this M state, and L is NL is the population of the lower state. So the rate of increasing of the population or the changing in the population depends on the different rates, right? So that depends on your B, that coefficient of stimulated absorbance, right, and your rho nu, energy density of your light radiation, and population of LH state, right? We are discussing about this process. So this stimulated absorbance, so that depends on the population of this, and coefficient stimulated absorbance. Right now what are the process that can happen, that is coming back through stimulated emission. So that process, the rate kinetics is P rho nu is the, suppose this is LM and this is ML, and suppose we are saying right now for this, our assumption is P nu LM is nu LM. Okay, LM is ML, and how it can degrade. So I am using a minus sign because for this rate it is decreasing the NM, right, and here it is gathering the population here. So this is a plus and this is minus, and another minus will become because of the spontaneous emission, right? This is the spontaneous emission. So that is depends on that, doesn't depend on the radiation. Acha, I have missed one part, that population of NM is there, and here for spontaneous emission we don't need any stimuli, right? So no radiation is there, so it will come back itself, and it will depend on the population of these states. Now I will not go into the derivation. I will quickly give you what we are going to get. We are going to get that Nm by N is actually B rho nu by A plus 2B rho nu 1 minus some exponential term, that is 2B rho nu plus A. So this derivation is already there in the lectures, so I will just go to the brief. And what I am trying to show here, that the ratio between the population of the M state and the total population will be given by a for a two level system. So it is very important, two level system. whatever we are doing now for a two level system, you are going to see the ratio is given by this equation. So at max, what can we expect? At time t, what can happen? At time t equals to 0. So t equals to 0, your exponential term will be 0. Exponential 0. So that is actually, let me write it like this. So at t equals to 0, what will happen? The exponential time will be exponential 0, that is 1. 1 minus 1, that is 0. So if we draw it somewhere, nm by n, and suppose this is with time t. So at time t equals to 0, the nm by nm is actually 0, right? Now with time it can increase, and will it increase monotonically or it will have a saturation? So do you have any idea, Jacob or Avantika, what will happen to this function? So at time t it was 0. Now it will increase monotonically or it will have some saturation. What do you think? Anyone? Are you guys getting me what I am trying to say? Is anyone there?
It should monotonically increase.
Okay, and why so? Why do you think so?
Otherwise, light will be attenuated. No? Only then light amplification will happen.
No, that we are going to see. If nm by nm, you are correct for that part, but let me interfere at that point, because actually, let me give a spoiler that for a two level system, spontaneous emission won't be that much high. So we cannot build laser from a two level system, because you are going to see that this will not increase monotonically. Actually, the highest value it can actually could have achieved, suppose at t equals to infinity. This exponential part is there, right? Exponential infinity. How can I tell it? I think I am missing some minus thing. Yeah, actually it will be an exponential minus. Okay, so sorry for that. So at t equals to infinity, you will see that this exponential all over this term is going to be 0. Okay, at t equals to infinity. But actually we are not dealing with t equals to infinity, what I have mentioned earlier, right? Because this is a perturbation problem we are dealing with. So t is not actually infinity, but it is more than 0, less than infinity. But let us discuss that what value it can achieve at t equals to infinity, if at all possible. So as you can see, then you could have achieved this value, b by rho nu. Now I have told you here, if b is equals to b is non-zero, then your a will also be non-zero. So if b, some value of b is there, then you should have some value of a. So actually the maximum possible value what it could have reached is actually half, 1 by 2. Okay, but it will not, because b is non-zero, so a will be there. So it will be something like it is actually will be let me draw you the curve for you. So it will increase, but then it will be less than half and it will get saturated, because a is non-zero. You are getting my point? So you will see that nm by nm will be less than half, and that is why. So these are the thing we are discussing, right? So this is suppose nm by n, what I am trying to say here, instead of pm by p. Okay, so as you can see, your nm by n is always going to be less than half. That means no population inversion. So nm by n is less than half, means still your NL is greater than NM, right? Because it is still half, less than half. Jacob, are you getting my point? What I'm trying to say?
Yeah, sir, I got it.
Yeah. So there will be no population inversion, and as there will be no population inversion, there will be some stimulated emission, but it will not, your stimulated emission will not, it will be less than your stimulated absorbance, and it is a net loss. But for you will see in the lectures that for a laser you will need a net gain, and for 3 level or 4 level system you can actually build lasers from 3 or 4 level energy systems. So these energy levels actually means you are having different molecules or different matters where there are if there are how many energy levels are there, populated or unpopulated, whatever energy levels are there. So according to that, suppose there is some material there is a 3 energy level system is possible or 4 energy level system possible. In that case you can make laser out of that system, but from a 2 level system you won't be able to produce laser. Why? Because your stimulated emission amount will always be less than your stimulated absorbance, because there is no population inversion. Okay, so now I'll draw some basic so I will not go into some basic let me draw some 3 level or 4 level system. And so what is discussed in actually in lecture 23. Okay, so suppose this is your 2 level system. Now suppose there is energy level, another state is there. Then let me write it, this is 2, this is 3, and this is the first one. Okay, suppose you are exciting your molecule to the second one, and there is some non-radiative process. I have to teach you one more thing before coming to this thing. So do you have any idea? Let me just keep another. I'll come back to this thing in 5 minutes, but before that I thought that I'll skip that part, but I will need that. Suppose your perturbation is gone, and suppose you have excited your thing. Suppose this is your upper state and this is your lower state. You have excited your molecule, okay, for some time. Then there is no excitation, no light. Now actually your stimulated emission coefficient will be 0, right? Because there is no stimuli, no perturbation, and no absorbance. So how can what will be your change in the population of the M state with time after perturbation? Suppose after excitation or something like that, after perturbation is gone, some molecule is there in the MF state, na? So actually you will see what would happen, that it should follow only ANM, right? Your spontaneous emission kinetics. But actually what was not dealt in Einstein treatment and other thing, that there could be some, so this is known as the spontaneous emission, for which you don't need any stimuli. And what is not actually discussed in many of the things, that is a non-radiative process. So these we always show wavy lines for that, and for radiative or those purposes we show straight lines, straight arrows. And for non-radiative, so this is known as a non-radiative process. Okay, so these are also active. So you know that my chart or your chart or all the things does all the thing show fluorescence or emission, or whatever we are seeing, that is really actually a scattering or something like that, right? So yellow, so if the wall is yellow, so it is absorbing rest all the color, and it is reflecting or scattering only the yellow to our eyes. So it is not actually fluorescence. Not all the things are emissive. Why is not that? Because we know that A can't be 0 if it is absorbing something, so it should have emitted something. But the thing is that there is a competitive process is always there, that is a non-radiative process. Heat, rotation of the molecule, or the vibration in the molecule, these are all non-radiative processes. Okay, so actually your energy absorbed can be dissipated in terms of heat also. So these are all non-radiative processes. So your molecule from the M state can come down through non-radiative processes also. So let me write it, non-radiative rate constant, and your population is M. So I am not writing rho nu, see, because the perturbation is gone, there is no stimuli. So these are the two processes that can happen. One is radiative and one is a non-radiative process. So you will actually see your rate equation will look like n0 exponential. So you guys can tell me that if you are understanding or not. If you have any doubt, you can tell me. So actually your decay of that excited state will follow a exponential condition like that. Okay, where your lifetime excited state lifetime. So are you guys did you hear about fluorescence lifetime, fluorescence? These are the terms you are do you know these things? Fluorescence, did you hear any time?
Sir,
Yes.
actually, A itself is spontaneous emission, which
Coefficient.
comes out, yeah, spontaneous emission coefficient, which is some non-radiative process only, right?
No, that is a radiative process.
Oh, okay.
So this stimulated emission or stimulated, suppose or spontaneous emission, these are all radiative process.
Oh, okay, sir.
Okay, so your this excited state lifetime is already given by, actually this we can also write in terms Nm equals to n0 exponential minus t by tau, where tau is your lifetime. So tau means 1 by a plus knr, or big or small, whatever you can write. And suppose you doesn't have any non-radiative processes, that time you would have expected something Nm equals to n0 exponential minus a t, right, something like this. So Nm equals to n0 exponential minus t by tau r, that is your radiative rate. Excited state lifetime, this is the normal thing, and radiative lifetime tau r, this is 1 by a. So in fluorescence part, when you will read fluorescence in future, you will see actually your tau is given by kr plus knr. Actually this your spontaneous coefficient is actually a radiative rate constant, right? So you will see something like this. And then again the fluorescence quantum yield, that part we have discussed in the first lecture or the second lecture. So that was I emitted, number of photon emitted by number of photon absorbed. That can also be written as, the intensity can also be written in terms of the rate. So rate of emission, right, and rate of absorbance. And you will see your at steady state, what do steady state means? Steady state means your rate of this excitation or absorbance, that is equals to your rate of emission, right? De-excitation. So that can be a radiative plus non-radiative. Okay, so that's why I said de-excitation, not the emission. So rate of emission is your ANM, right, and your rate of absorbance or excitation is your rate of de-excitation, that is A plus KNR and NM, right, that is your A plus K nr plus a, suppose it is something like that. Okay, it is also written like this. And so in assignments there can be some numerical problem based on this. I am not sure if there is some problem like this, or you can see something like that. So from here one concept you can understand, that your quantum yield or emission quantum yield can be 1 means 100%, right? Whatever you are what is it is absorbing, it is emitting all. So very few dye or very few molecules can actually do that. And when it can be 1, when the radiative rate will be almost 0, right? There will be no non-radiative processes. Then you will see your phi f will become a by a when your knr will be 0. So that's why in most of the cases what you see, that suppose I have my laptop or my book, something like that, or any material that is not emissive, that means yes, there is some spontaneous emission part is there, but the radiative rate constant is very high, and that is why our quantum yield of the emission is very less. Okay, that's what I was trying to say like that. And now we can go to that the 3 level or 4 level systems. Suppose you are, so absorbance is also a radiative process. Okay, so whenever I am showing arrows, straight arrows, those are radiative processes, and when I am showing wavy arrows, that is a non-radiative process. Okay, so suppose so this is a radiative process, and then from second state to third state, suppose it is going through a non-radiative process. So what will happen, that just quickly after excitation, suppose there are 10 molecules here, 1 2 3 4 5 6 7 8 9 10. Okay, 10 molecules are there in the having the energy in the ground state. Now it has been excited, and quickly that non-radiative process are very quick. Okay, so due to that, what is actually happening, that, and another condition is that the from 3 to 1, so this is actually a forbidden process. Okay, so these are all we are assumption that at what point we will get the population inversion. Okay, we are going towards that population inversion so that we can get laser. So actually suppose you will see in Jablonski diagram or in energy states later in electronic spectroscopy, suppose this is a singlet state, this is again a singlet state, and suppose this is a triplet state. You know that singlet to triplet, these processes are actually forbidden process, spin forbidden process, this transition. So actually it will take time. So it actually takes time because the population thing is required, population inversion and the other thing. So suppose what is happening, that from 1 to 2 there is some emission, a absorbance, then 2 to 3 it is quickly coming through a inter-system crossing process, that is known as that is a non-radiative process, and then suppose it should have come from 3 to 1, but it is a forbidden process. Okay, so it is not coming. So with time what you are going to see, that just after some time I will draw the picture of that. You will see only 4 or 3 are here. Okay, S1 or not S2 I should not say, and suppose this is the third state. So you will see at some point of the time your rest of the 7 molecules are there in the third. Then what you will see, there is a population inversion, and then your normal radiation won't be possible because your NM part was also very less. Okay, so what is the rate of this process? So this is B nu L rho nu and NL. NL is very high at this point, B rho nu NL, N1 actually you can say, and this process is B, because we are talking about only about the spontaneous thing, right? Rho nu N3, but N3 was very less at the beginning, right? Nothing was there at 3. So and with time also it will be very less. But after some time, after excitation, the population of the state has increased in the state 3 than the 1. Then what you will see? You will see a pulsed laser operation, so, or the stimulated emission. Okay, so this will give you a laser system, 3-level system. And what is the thing? This is a, you will get a pulse laser out of this. Why pulse laser? Because after some time the population inversion will take place, and then only it will shoot the laser or give you the stimulated emission like that. So it will be something like this. So after some time, so then after for some time it will be, there will be no radiation. Then again after some time population inversion will happen and it will shoot you something like that. I hope you are getting this point. Are you getting this?
Yes, sir.
Okay. So you read rest of the 4th level or 3-level system, what other processes can happen from the lecture, and in assignments you might require them, that what kind of are you going to get a pulse laser or you are going to get a continuous laser. Continuous laser means with time, no matter what, you are getting a constant intense stimulated emission. Okay, so let me draw the situation for you for a 3-level system. Suppose this is 1, 2, suppose 3. So 3 energy level system. So this 1 to 2 absorbance is possible, and suppose from 3 to 1 all the things is possible. Means radiative rate is also possible, non-radiative is also possible. Okay, radiative or non-radiative, whatever is possible. Means, and the problem is that your from 2nd to 3 it is a forbidden process, suppose. So what you will see, that just after the excitation you are populating your 2nd state, but if something is coming to the 3rd level, it is not staying there for long, so it is quickly coming back to your ground state. Okay, so now the population inversion can be created between your 2nd state and the 3rd state. Okay, and for there you will get a constant laser stimulated emission. This will be a constant thing, constant intensity. Means it will not be a pulsed operation. Why? Because anything what you are exciting here, it can come back to 3, because 3 there is no population and you are creating some population at 2. That means the population of 2 is greater than n3 at any time, right? Then you are getting a net gain in the stimulated emission, and you can produce continuous laser from that 3-level system. So what you are currently seeing, depending on the kinetics or what are the processes involved, from a 3-level system you can create a pulse laser also, and you can create a continuous wave also, continuous laser.
Sir, but again,
Yeah.
the population inversion can happen between 3 and 2, right?
How? Because for this system you are saying, or this one?
The last one.
The last one. See, from 3 we are saying that non-radiative or radiative processes are very active. So just after reaching to 3, the molecules will quickly go to the, using non-radiative or radiative process, it will quickly go to the energy state 1. So it will not go back to 2.
Okay.
And for it is, if it is going back to 2, then it will be a stimulated absorbance. So you are not getting out of it. Means you should, for laser, your emission should get out of your molecule, right? So if it is absorbing something, that means it will be stimulated absorbance.
Okay. In case of the first and second diagram, the radiative and non-radiative process weren't that active.
No, from 3 to 1 it is actually a forbidden one. So you will learn,
that is in first question, right?
first and second, these two. So these two.
Sir, then I had a question.
Yes.
If 3 is a triplet state in first and second diagram,
Yes.
okay, then from 2 to 3 transition, how is it possible?
So,
Because
so
that is
that is
also spin forbidden.
that is also spin forbidden, but with time, that is what I am saying, that with time, so whatever forbidden means that TMI is 0. Okay, you will
Hmm.
see mathematically TMI will be 0, but you will see that it is actually possible. So in spectroscopy, forbidden means the intensity is very less or the process is very slow.
Okay.
Okay,
Hmm. So
with
3 to
time,
3 to 1 is also possible.
yes, the 3 to
1 is also possible because
also
that.
possible, but the energy state, this energy, as you can see, 2 to
Uh,
3 for ISC,
hmm.
it should be very close. My scaling is not really proper, but
Okay,
if you
okay.
see Jablonski diagram or something like that, actually
Yeah.
ISC is a non-radiative process, and
Hmm.
non-radiative processes are much faster than the radiative process. Okay,
But actually, it is decrease in energy, right? I mean,
decreases energy.
it is not going through any energy barrier. So, however the high the energy barrier is, it is
Yes,
just going down to its ground state or
yes,
one energy state one, which is lesser than energy state
you
three.
are
So,
correct. You are correct.
wouldn't that be an issue? Like, even though it's a slow
So
process.
when you will see this thing in perspective of the quantum mechanics, you will see the TMI from suppose this is a singlet state to a triplet state. Even if second to third, means you are saying from a 2 is at high and 3 is in lower energy,
Uh-huh.
why it is a forbidden process even if the 3 is lesser energy than 2. Actually, you'll see that for a triplet state and for a singlet state, ideally there is not emission because the transition moment integral is 0,
Hmm.
not energetically. So quantum mechanically it will be 0, and the thing is there will be a mixing of states, what we are discussing actually. So it will not be ideally a singlet or a triplet state, so it will be a mixture of a singlet and triplet state where we will get the phosphorescence. Okay, so I am not going to that deeper into that part. So whatever phosphorescence we are getting from a 3 to 1, or what we should have got, is actually coming from a mixture of singlet and triplet set, not a pure singlet or not a pure triplet. From a pure triplet to pure singlet, the process is forbidden, but from a
Hmm.
mixture of states, it will be possible.
Okay, okay.
So these will actually are not a part of this curriculum. Actually, for a detailed course in fluorescence, it will all be discussed, I guess. You can what can I suggest you to read for this part? What did I read? um, you can always go back to Lakoich. Lakoich, this is called a Bible of fluorescence for our, generally I am also working in fluorescence spectroscopy. Okay, ultrafast dynamics and other thing. So we treat this book as a Bible of ours. Means all the, or means not all, but is very relevant. So for fluorescence spectroscopy, these kind of things you can always go back to Lakoich and read these things, that what are, I mean, what I was trying to say actually. I think it is also there in Banwell for a electronic spectroscopy. When this part will come, I think that will be discussed. Do you know something regarding heavy atom effect and other thing? Heavy atom
Mm,
effect.
no, I don't.
Okay, so you will see that heavy atom effect is worked as a perturbation. So that perturbation, what it will do, it will try to mix singlet with triplet, and due to that, in presence of the heavy atom, your fluorescence will quench. The fluorescence is singlet to singlet or between same multiplicity. So for now, let us consider only singlet to singlet. So you will see that heavy atom means suppose what I can say, iridium or that kind of atom, which is atomic mass is very high. So that actually act as a perturbation in the energy field, energy dynamics of those electronic states. And when those heavy atoms are present, you will see your fluorescence will quench, your phosphorescence quantum yield or phosphorescence will be active. Okay, So you can look for heavy atom effect in this concept, heavy atom effect. I think in Banwell you can find also, you don't have to go to language. Okay, please look for this thing, heavy atom effect in fluorescence spectroscopy. Okay, I think you will get that. So I am not discussing the 4-level system because it will take some time. How much time do we have? We have another a few minutes. I'll just quickly write one message here. Sorry. So what I will not go into the deep, means I will not discuss the 4-level system. So next, Eyring equation was discussed, lecture 24. So there I am not writing the Eyring equation, but why Eyring equation was invoked, to show you that a faster process, means how fast a process can be in a, means energy reaction kinetics. So Eyring equation is a very important thing, parameter there, where the rate is, let me write it, or else e to the power, suppose delta g for a equilibrium process or a standard RT for a transient state, and there are some partition coefficients involved, where A and B are the reactant and your AB is the transient state. Okay, these are all come in a transition state theory where it is being discussed. Let us not go to there. Let us think just your all partition coefficient is 1. Let us think like that, what can be ideal situation, and there is no energy barrier from A means reactant to your product. So your delta G, that dagger is also 0. So your this exponential term, this also gives you 1. So you are right now have K, your rate is equals to your Boltzmann constant into temperature by your Planck constant. So from there what you can get is here actually your K can be at room temperature, that is 300 Kelvin. You will get 6 into 10 to the power 12 second inverse at 300 Kelvin. And your, so as we have discussed till now, your time, that how much time it will take. So your that is 1 by rate constant, right? What we have till now discussed, you will see it will take around 170 femtosecond, something like that. So that is actually we want to see using laser. So the, what are the fastest, means the bond breaking or these thing we want to observe, and that is known as ultra fast processes. Okay, ultra fast processes, right? Because 170 femtosecond is really ultra fast process, right? So and also known as ultra fast dynamics. What actually is my domain of work, my doctoral work at IIT Bombay. So I am a student of actually Anindya sir, who is teaching you. He is my professor here also. So these are the things we want to see using laser. So the previously we have set up that how lasers can be prepared or at what things are required. Now we are going to see that how using lasers we are going to monitor this femtosecond processes. Okay. So in actually lecture 25 and 26, what has been discussed is the transient absorption spectroscopy, that how using lasers we can study this bond breaking and those things. So did you study that part from the lectures?
No, I couldn't go through that.
Okay, so I'll just give you a brief idea, and you can later, before solving, obviously before submitting. Acha, lecture, these are all lecture 5 or lecture 6. I have moved into lecture 6, I guess so. Is it lecture 5 or lecture 6? Oh no, I am not yet lecture 6. Oh my god. transient spectroscopy, huh? Also known as palm probe spectroscopy. Okay, so today we will not, I think, be able to discuss the questions, those extra questions what I have. We will discuss that in some other class. So let me quickly give you an idea what is a palm probe spectroscopy or a transient absorption spectroscopy. So again, suppose there are two states like this. Okay, this is your ground state, ground electronic state. This is your excited state, and suppose there could be another state. It could be triplet, it could be singlet also, right? There are multiple states. So what generally we expect, that just after the excitation, how the second one will decay with time. We showed you that it is an exponential decay, right? Am I making sense what I am trying to say? Suppose just after the excitation, suppose at this t equals to 0, it is getting excited, huh? And then just after the excitation, when there is no other thing, then your second state is depleting. Now how can we observe these dynamics? How can we particularly say that we want to see this process, what is the time is taking or lifetime will count from here? How can we see that? So what we can do that, so this is the pump, right? So just after pumping your molecules to the thing, suppose we are using another, so it is known as pump probe spectroscopy, right? So there are two excitation source. One is known as pump and one is probe. Probe means what we are going to observe. Okay, so suppose with pump we are exciting our molecule from 1 to 2, and suppose then it can come back to, it can go to 3, and it can emit from here also. So generally what do we expect for 3? Can you tell me? Suppose at 0 second only we are exciting, right? T equals to 0, not second, suppose t equals to 0 time, so we are pumping. So just after the pumping, your excited state of second is coming like that, exponential. And what do we expect for 3? Can you tell me, Jacob?
It is 0 and then it keeps increasing.
0, after 0 it will keep increasing, right?
Then
Yes, because at first, see, population of two state after t equals to time 0 means after the excitation, it is possible that your all the molecules are here in the 2, then it is coming back. It can also come back to 1 also, not only to 3, right? And for 3, just after the t equals excitation, there is no molecules, right? There are no population was there. But when you have excited, then there is possibility that just after t equals to some time, your population coming to 3, then it will hit a maxima and it will then decay. And decay is also associated with this. Means suppose the decay will look like, so this is known as rise time, and then again so this is very poor drawing skill. Achha, do I have the eraser here? Yes, I have. I will erase some part. Okay, I will draw again. So first it will rise, then it will follow the exponential decay, the third step. Means it will also follow exponential thing, but first it will rise. So this is also known as rise time. Okay, so this is in another excited state phenomena that can happen, right? We can look after. But how can we actually see these things, or how can we actually so these are the processes what mathematically we can say that these are the thing happening. So what we'll actually use, so this pump laser, that is very high intense. Okay, now we high intense or intense pump laser being used, intense pump. Now we'll use uh, weak probe light, okay, probe laser. So what that will do, so from 1 to 2 there is some population has come here, right? And these are the things we are dealing just after the when the perturbation is not there, right? Means the perturbation is gone. Now what we are applying some weak probe laser to interact with the second state. Suppose this is a virtual state or something like that, whatever electronic state is that we are
Sir, actually, I had one question.
yes.
Why is at t equal to 0? It is kind of infinity.
Where is infinity
I
t?
mean, it's a just one line.
So I am not means what I am trying to say that we are saying that so at this moment so these are all being excited, and just after the excitation what is the behavior of the excited state population of the second one. So I have shown you here, right, this slide that it will follow a exponential trend just after the perturbation or when we have removed the perturbation, something like this.
Oh, that straight line is for perturbation.
Yeah, so until that point of time it was interacting with the light, and then it is not interacting. So whatever
Oh,
lasers we are using, these are all pulse laser. So this
okay,
pump,
okay,
these are all pulse laser.
okay.
So it is interacting for a very small time. Okay, so it is
Yeah.
interacting with a high intense, the intensity of pump is very high, but it is interacting for very less time. So with a high intense, what we are trying to do, that we are trying to create a high population at the excited state, not really a population inversion, but what we are trying to say is that we are creating some we are taking some population to the second state. Now with a weak probe we will try to interact with the second state, not with all the excited state molecule but one or two. That's why we are using a weak probe. What they are saying that with weak probe what we can happen, we are giving a suitable energy that it can go from 2 to 2 dash, suppose, or suppose if there is some population at 3, suppose some population is there at 3, so we will give a suitable energy, that is our weak probe light, then it can go to 3 dash. Okay, so what we can observe, then we can observe the absorbance of state 2 or absorbance of state 3. Now your absorbance depends on the epsilon cl, right? Epsilon c of second state, right, and L, and suppose it is depend on the C3, that is your how many molecules they are at your energy level 3, right? So we are actually at the detector we are observing the probe light, not the pump light. Okay, probe light we are observing. So suppose we are giving a I0 incident, that is your intensity of the probe light, which of a monochromatic light. Okay, this is a monochromatic light again. Actually it is not a monochromatic light, what you will see, but suppose this is a monochromatic light, so it can only absorb of certain energy like 2 to 2 dash or 3 to 3 dash. So these are not to the scale, so the energy can be different. Okay, so 2 to 2, suppose some probe light will absorb 2 to 2 dash, some will absorb 3 to 3 dash, but suppose
Sir, the light that we use is called probe light.
we are using two kind of lasers, one
No.
pump to excite our molecules, then we are interacting with a weak probe. Weak means the intensity is very less, so that we
Okay.
are going to visualize at the detector.
Okay, okay.
And
So, why is not the pump? Or where is the pump and probe used?
so same, so suppose this is your molecule. Okay, first your pump is being there, we are exciting with a pump light, pump, then just after the excitation at different delay times. So actually the thing is like how can I tell you, so suppose these are all in optic tables, huh? So this is your sample, your pump light is hitting, so there is a path for the pump light, okay, and there is a path for the probe light also. So suppose there are some mirror things are always there. So what we are doing, your pump light we are keeping one thing constant, one path constant, and we will vary the probe light, okay, by varying your this we will
Okay, okay.
vary this delay. So your probe light will come from another angle or somewhere another, and it will fall onto
So
your sample.
probe angle and intensity is also varied,
Yes. So your
and that is detected in our detector.
yes, because your probe light will be absorbed by the excited state.
Okay, okay.
So
So pump is like kind of my reference kind of thing. I am keeping it
no,
constant.
it is not actually a reference. Pump is only being used to excite your samples. It will not be detected. So in
Okay, okay.
absorbance, you have seen that your um, at the same time or interval of some time your I0 and IT are detected. But here your pump light will not be detected at the detector. Only the probe light will be detected.
Okay, so sir, in that graph you told no,
Huh.
there was a straight line after a particular t tending to zero, that time interval,
Mm,
like which indicated the perturbation.
yes, yes,
So that perturbation actually was created by this pump.
yes.
Okay, and then the further detections from the machine happened due to my probe.
Yes, but that probe is also taking your molecule from second state to a higher state. But
Uh,
the very few molecules it is taking. So
okay.
from the
But the initiation happened because of the
the
pump.
pump. So
Okay.
we are so we will not see the ground state dynamics. We will see the excited what is happening at the excited state.
Okay, sir. Now I am clear.
So this absorbance, so now it will be interacted with a weak probe light, and that will be detected. So detected means it will the absorbance of it will be detected. IT minus I0 something like that, or IT by I0, right? Absorbance is what, log of minus log of or log of IT by I0, right? Not minus, log of this, and that is your epsilon CL, means it will depends on the excited state concentration or excited state lifetime, excited state population. So what is actually going to happen, let me write it here, show you here. So suppose this is your, due to your pump light, your population should follow this line, what we are expecting, but we don't know, right? Now suppose a probe light is coming and interacting with it. Suppose it is coming, so let me use another color, green one suppose. So suppose it is coming before you are exciting your molecule, huh? So this is your, so before you are exciting your molecule, here you are exciting, but exciting for a very less time interval. That is why I am all these thing are a line like thing I am drawing, okay. So these are lasers, pulse laser. So your probe is also a pulse laser. It is, so what we are going to do here, we are varying the delay time of the probe. So it can come before your probe also, before your pump, and with the pump also, anytime. So suppose here your probe light is coming, okay. Now so there is no intensity, right? At the second state there is nothing, so it will not interact, means it will not give you any signal. So in absorbance you will get zero, so there is no light absorbed. So this, but suppose at this point, so when it is at the same time coming at the same time with the pump, so you are expecting your absorbance should be very high, right? With the so your transmittance will be very less. At this point of time your second state is highly populated, and as second state is highly populated, then your 2 to 2 dash transition is also going to happen using the probe, right? So it will absorb much, so you are going to get a less, so suppose you are going to get your signal like this, so your absorbance, so at this point your absorbance will be high, then with time it will going to follow this decay kinetics, what earlier we were not able to see, right? Because as your population, because what I am saying that your absorbance is depending on the population, right, of this second state, suppose absorbance of the second light, right? So with time your second state will decay, the red one. So at t equals to 0, absorbance of the pump light was maximum, right? Because that time the population was maximum for the second state. Now with time n2 will decay and absorbance will follow the same curve. Is this making sense what I am saying?
Yes, sir.
Hey, you can always go back to the lectures and see. I think Sir would be a better teacher. So anyway, so now for the third step, suppose we are using a different probe light. Okay, so which will measure this thing 3 to 3 dash absorbance. So what we will see that just after, so before the excitation, no absorbance of your second probe light, that is A3, huh? That also depends on the population of the N3 state, right? So at time 0 also, when your probe is coming, you will see that there is no population at 3 state, so no absorbance. But with time, so as suppose, and these golla things, round things, means here the probe light is interacting with a probe light as coming as a delay. So these, the x-axis is also known as delay, huh? T, and here also delay. So it will come at certain difference that is created using that retroreflector and other things. So I am just drawing. So this is the, your probe light is coming after certain time, after some delay, right? And it will follow this. At this stage it was here absorbance, there is no absorbance. Now your absorbance is getting high because with time your the population of the 3 state is being built, and then it is decaying following your excited state dynamic or kinetics of this third state. So earlier we are not able to visualize the decay. Now we are able to visualize this decay or the excited state dynamics. Are you getting my point? What I tried to convey? So this is how actually the excited state processes are being shown, or being, we can see those things. Next, it will be better if we go to, I think, like 1 second. So is there any doubt? So Jacob, I will recommend you to read this part at first from the sir's lecture, and then go to the Ahmed Jewel's experiment what sir has discussed, that snapshot of bond breaking and how those things can be visualized. We can anyway discuss that part in the next lecture. We'll solve some assignment problems. Avantika, do you have so did you understand this part, or did you read this part earlier from the sir's lecture, week 5?
Yes.
And did you understand the bond breaking thing and the other thing, snapshot, how those things are being
Yes.
monitored? Okay. So Jacob
Yeah.
and Avantika, we'll do this snapshot of bond breaking and this Ahmed Jewel's experiment on the next day, when Jacob is already read that part, means the transient part. Then it will be helpful for him, I think, to understand that part. But now what we will discuss, I will quickly discuss the week 5 assignment. Okay. Okay. So one by one you can so I thought actually I will discuss the week 6 lecture also, the Raman spectroscopy and the symmetry part. But the next day, what I believe that Raman scattering is very easy thing to. I mean, Sir has taught it very beautifully. So I don't think you will need much more explanation there. I will just quickly do that, and we'll do the rotational spectroscopic mathematics. What is left today, we'll do it tomorrow. So anyway, so let us solve these things. This assignment problem, that two level systems cannot be used to make lasers. What do you think? Any one of you can answer, or two of you. So
Population inversion can't be achieved.
yes, so this actually is a correct answer, right? So this is the right answer. Okay, I will change my color to red. Okay, now second question is A and B are Einstein coefficient, that what we are discussing, of spontaneous and stimulated emission, and KNR is the non-radiative decay rate constant. So lifetime of an excited state after light is switched off is the inverse of. What do you think? So they want to know tau. What is tau? Tau is dependent on something. What is
A plus KNR.
Yes, the B term is not included, right?
Mm.
Yes, the B term is not included because light is switched off, right? After light is switched off, that means there is no stimuli, and no stimuli means no stimulated thing is there. So it is like that. So now the third, intrinsically pulsed operation is achieved for the systems with, what do you think? We have discussed it today.
Three energy levels.
Three energy levels, right? So this is what we have already discussed. Now the fourth question. So what do you
Sir, why not with 4 energy levels? In that also you can inter levels can populate the energy levels, right?
Yes, actually it could have been, but for that I need to explain the four level also. So the four level system discussed in the lectures, I guess these are the assignment based on the lectures. I think in the lectures, the fourth level system, what is being discussed, actually it was shown as a neodymium YAG laser. What is actually was a continuous laser. That's why I guess only the three energy levels is here, because in the lectures I think it has been taught like that for a pulsed and the continuous three level energy levels were discussed, and for a four level I think the continuous is only discussed.
Okay,
I think
sir.
if dynamics can be varied, then for a four level system I guess we can also get a pulsed operation.
Yeah. Okay, sir.
Okay, now what do you think about laser light? What is laser light is usually, what do you think? Is it a monochromatic source?
Yes, sir.
It is intense, as I told you, because it is a pulsed, right? Because we discussed about the pump probe where we need a, so we can vary the intensity also, right? Depending on the different kind of filter we can use. So these two are correct. What do you think about the other two? Is it a coherent or highly directional? Actually you will see, actually these are coherent source. A coherent source means how can I so let me check how to coherent. So what do you mean by coherent? Can anyone tell me?
If the phase difference is changing in time, then it's coherence.
Yes. So for laser light you can actually do that. Actually,
Yeah, in
laser,
pulsating lasers they do.
right? So we are discussing about that pulse laser and the frequency of that. So actually this is actually a coherent source pulse laser.
I didn't understand the highly directional. What is directionality here?
Directionality means, suppose so normal light, so it diffuses, right, with so have you seen a laser pointer?
Oh, yes.
Why do we use it as a pointer? Why not a torch? Means I am just trying to give you a rough idea, rough estimation what I am trying to say.
Oh, it is not diffusing much. It remains
Yes,
as it is.
yes, with time or with distance it will not diffuse.
Okay.
Okay, So that's what it is trying to mean, highly directional. So whatever lasers we actually use in this palm probe spectroscopy or other optical thing, spectroscopic thing, actually are very different from laser pointer. So what do you think, is the laser coming from a laser pointer, is it a continuous source or a pulsed operation?
That depends on the dynamics of the system, right?
Actually you cannot, you can use a pulsed laser as a laser pointer, but then it will burn your actually the slides also, or the, what can I say, the cloth or something like
Oh,
that, because pulsed laser have very high energy. Okay,
okay.
the continuous laser don't have that high energy. Okay,
Okay.
so let us go to question number 5. So time to break a bond typically is, so as from Eyring equation on the rate constant we already know, right? This is in femtoseconds, 170 something like. And if you read that Ahmed, so I should say Professor Ahmed Jewels, Professor Ahmed Jewels experiments, you will see that he has found out that bond breaking of a ICN bond, okay, in a ICN, you will see he has reported that it has took 205 plus minus actually 30 femtosecond. So, so these are the groundbreaking work have been done with lasers. That is why he has been awarded with Nobel, I think in 1999. Professor Ahmed Jewel. He is a Egyptian American scientist, and very 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 famous. I think when you will means learn more about the laser, I think Sarah has shown his picture also, so you will see that in the lectures. So let us go to the second question, question number the sixth question. So in a typical palm probe spectroscopic experiment, palm and probe lights are respectively, what do you think?
Weak.
Pump is strong.
Strong and weak.
Strong and weak. So
We,
can anyone tell me why
And probe is weak.
and
Probe is weak.
I can't hear you that you what you say. Can you repeat again?
Strong and weak.
Strong and
Pump
weak.
is strong and probe is weak.
Yes, yes, correct. But can you tell me why pump is strong and why probe should be weak?
Because pump has to excite from say energy level 1 to 2, and the probe has to excite from energy level 2 to another energy level, but it has to be weak because it should not excite it higher into the higher energy level,
Yes,
so
means
that's
it
why.
should not higher, means what it should not do, that it should not deplete the so what I was trying to say from this.
Population of,
Yeah,
yeah,
so it
population
should
of the
not
protein.
alter this population highly, then these dynamics will be changed, right? This red one, so it should interact with, suppose there are 5 molecules, so these are all assumption, means what I am saying, 5 molecules. It was not like that, right? So suppose it has so in excited state there are 5 molecules, the second excited state. Now suppose when the probe light is interacting, we are using a weak probe so that it can interact with only one. Okay, means I'm just saying the number are all assumption. Okay, so just a rough idea. If all the 5 are being go to 2 dash, then the next decay kinetics will also change, right? The red one. So that's why the excited state population should not be altered with the probe light. A very few of the excited population will go to 2 dash if we use a weak pump. That is why the pump is weak. Okay, I hope that is what you are trying to say. So did you understand, Jacob, what we are discussing here?
yes, sir.
Okay, okay. Now we will go to question number 7. Question number 7 deals with the palm probe experiment. So what do you think? Negative absorbance signals are observed for acha. So this is a palm probe experiment thing. So I don't expect Jacob will give this answer because I also didn't discuss this part today. But is Avantika, did you search regarding this palm probe experiment, and can you tell me that what this question, what would be the correct answer or something like that? If
Yeah, actually, I did it. I only chose stimulated emission, so my answer was also not totally correct. I mean,
Yes. So Jacob, what I am trying to say here, this so tomorrow we will discuss. Tomorrow means the next day, Raman scattering. So we will not really discuss the symmetry first few lectures. Maybe if you have any doubts, so I am just writing. But before that, we will discuss this palm probe business once again, and these processes, this ground state bleach or transient absorption is also known as so the whole spectroscopy is palm probe spectroscopy. Okay, now one of the process is also transient absorption. Transient absorption means excited state absorbance. Okay, something like that. So why excited state absorbance? Because it is exciting from absorbing from 2 to 2 dash, something like that. I write right, 2 to 2 dash. So that's why it is known as excited state absorbance. And why it is known as transient? Can any of you told me why it is known as transient? What do we mean by transient? Why it is known as transient? Actually, why? Because transient means it is forming for a very less time, right? And then it is decaying. So this process we generally, so for 2 you see that there is a decay, and for a 3 state population, in the 3 state you see that first there is a rise, then there is a decay, right? So these are all kinetics, decay kinetics, right? How it is decaying. But here you see there is a rise, then there is a decay. So we actually call this thing as transient. So you know this transient species, right? Forming for a very less time, then from a product it is going to a reactant state, right? Transient species. So this is something like that. So this excited state, the second or the third, right? So these are, we are calling it a transient species, from which if absorbance is taking place or excited state absorbance is taking place, we call it a transient absorbance. And then so actually the answer will be a ground state bleach and stimulated emission. We will discuss this thing using a image. I have what I have. I will discuss it in the next day. Okay. So question number 8. So in order to get a femtosecond resolution in a palm probe experiment, the pitch of the screw on which the translation stage is mounted has to move with a resolution of, what do you think? That what should be, how much distance should you move for a femtosecond resolution?
microsecond. Oh, sorry, micrometer.
Micrometer, right? So I will just give you an brief idea, that suppose 3 into 10 to the power 8 meter per second is the velocity of that laser, right, in the light, approximately, right, meter per second. Suppose we want a 1 femtosecond, that means how much in 1 femtosecond, how much distance the light will go? What do you think? And your suppose this delay is also something like this. Okay, so your light is going to a retro reflector, something like this. Here are the mirrors are kept. Okay, so actually what you will see, so let me write it like that. So we are creating a delay like this. So actually the light is going d distance and it is also coming back, right? So actually it is going a 2D distance. So this distance is very minute, distance between two mirrors. Okay, so actually the light will follow a 2D distance at some time. So what I was trying to say, so this is the, so suppose we are giving a delay of t femtosecond. So at t femtosecond the light will actually go to 2D distance, not d. Okay, because it is a, in delays we using a retro reflector. Retro reflector means two mirrors are like this, so that we can get a parallel beam of light. So we are hitting there and it is coming back, and these mirrors are on a stage that will move, so on a mounted on a delay scale. So it, for using some pitch of the screw, it will move. So you will actually see at 1 femtosecond it will actually go to 2 meters or something, 2 feet, something like that, 2 feet I guess. I actually don't remember. So let us calculate. 1 femtosecond, how much will go? 3 into 10 to the power 8 meter into 10 to the power minus 15 second meter second inverse, and second inverse go 3 into 10 to the power minus 7 meter, right? And that is how much? 0.3 micron, right? Micrometer. And that is actually am I writing it right? Yes. So as you can see that if you, and 1 femtosecond thing, then you actually, your 2D will be 0.3 micron. What I can you able to understand what I am trying to say? That suppose you want to have a delay of 1 femtosecond, then it will go through this distance. So your screw should be something like that, that it can actually manage that part. So actually this is in micron. Do you have a question number 9? No. Actually what I thought I will do, I showed it to Jacob that we were going to solve some rotational spectroscopy problems, okay, from Banuel's book. So this is chapter 2, okay, as you can see, chapter 2. So I will urge you to solve this problem, Avantika and Jacob, so that we can discuss in the next class. If you have any doubt, again we will discuss that. This 2.3, 2.4, very beautiful problem, all based on those equation that has been taught. So you will really enjoy these problems, I believe, because I was solving it yesterday night, and these are really beautiful.
Sir, the equation needed was for the Professor Ahmed's experiment,
No,
right?
no, 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 no. These are all from rotational spectroscopy. So rotational on microwave spectroscopy.
Oh, okay, okay.
That
Fine.
rotational constant B is 8 pi square IC, right? And your energy is B into J plus 1.
Yeah, yeah. I remember.
Gap between two line is 2B J plus 1.
Uh-huh.
These formulas.
Okay, okay.
So did you solve those problems earlier from Manuel's book, or any other book? Are you trying to solve any numerical problems? Jacob and Avantika, anyone? So what we will try to do, that we will solve this problem next day. Next day we will begin with this problem, and then we will go to the study material for week 6 and week 6 assignment, because I believe week 6 Raman scattering, the first part and the symmetry part, I think it is easy. I guess we will get it. If not, then we are here to discuss, right? So today we'll stop at this point. Okay.
Thank you, sir.
Okay. So
Okay, sir. Thank you.
yes. Happy Holi, guys, and
Same to you.
yeah. for joining.